talking about the class of machines that we have available to us. And there are some very, very large machines internationally. And even within Australia, we have some reasonably sized machines providing different sorts of performance. So classic HPC in a tightly coupled parallel machine is, of course, where supercomputing has been to date. It's where UQ has had some resource to date. It's where the national compute infrastructure is in terms of supporting very tightly coupled, highly parallel computing. Nationally, we also have a research cloud, and we have a node of this in Brisbane, which is really supporting high throughput computing much better. Now, that's not to say that you can't do this. In fact, I know if you look at the load on supercomputing centres, you see, you know, in our case, it can be as high as like 70% or more of the jobs that are running through that are actually high throughput. And that's fine, but it turns out running those on cloud infrastructure is a much cheaper way to achieve high throughput. And so we really have an opportunity for us to single out those workloads and send them to the right places. So in sizing FlashLite, you know, we only had 1/10 of the budget of Gordon, but we're deliberately taking some of our load, which we would call high throughput, and move that to resources where there's a cheaper solution for that. You've heard quite a lot then about massive memory and the way you can do memory aggregation, and so that's driving the design of FlashLite, as is the high I/O throughput. So the research computing strategy at UQ is very much about directing these jobs in the right places, rather than trying to run one system that necessarily serves them all. So let me just spend a few slides pulling that out a little bit more. So traditional high-performance computing sits, and Mike mentioned Flynn's taxonomy before, sits on a couple of different processor models, and you can go to market and buy any of these. So traditional shared memory machines, in which I have perhaps non-uniform memory access, but cache coherence across the machine. This is the class of machine that we've been running at UQ up until now, allows us to write applications using libraries like OpenMP and do loop threading, in which every processor can touch every bit of the memory. And we rely on the caches to, in fact, make sure that the stuff we need is close to the processor. Everything relies on caching these days, even the sorts of systems that we're talking about with VSMP, and I'll come to that in a moment, rely on you being able to get locality of access. And some of the optimization that people do is to sweat blood on getting that to happen. Of course, most of the parallel machines, most of the high-performance supercomputers around are these distributed memory machines, in which processors are attached to memory. We can send messages between processors, and it's up to the programmer to decompose that. And so you have to program in a different way using message passing, and libraries like MPI do that. And so the machine that Gordon is and the machine that FlashLite is somehow trying to pull those together using some software abstractions. I might just skip that through. I did say something about high throughput computing. As I said, a very large fraction of the load on the HPC resource at UQ has been really just high throughput. I want to explore what happens when I change these things. I want to solve all these molecules. I want to solve all these proteins. And we now have a reasonable resource in the cloud infrastructure in order to serve those. So we're standing up resources that will allow us to do a very large number of what are largely sequential jobs, but stream them through the machine efficiently. So when the application groups think about the resources available, we need to be thinking about the bigger picture and sending things to the right places. We're seeing a significant load for machines that are not very parallel, as Mike has outlined, but require very large memories. De novo genomic reconstruction is called the quintessential killer there, and we've tried to factor that in to support those efficiently in FlashLite. We've had a small number of large memory nodes, and the big question is, when you're spending money, is what's the optimal size and how many do I get? And so we've had 3 large memory nodes dedicated on Barine for doing these sorts of jobs. but it's a very hard resource to manage. 3 is not right, is 6 right, how many do I buy? And then you find that they're actually getting underutilized. You can parallelize these jobs to do message passing, but that's not for the faint-hearted. And so, again, as Mike has highlighted, sometimes it's better to just go sequential and get through the job and get it done, and then move on to the next one. Some companies will sell you a cache-coherent, non-uniform memory access machine, and they work as long as you can get the cache locality there. But if you don't need that, then you're paying for cache coherence hardware, which is incredibly expensive. And so, like Gordon, what we've done is we're running this VSMP software that does distributed virtual memory. It's distribution between the nodes, so paging occurs between the nodes. But I just want to keep stressing, there is no free lunch when it comes to locality. So programmers still have to make sure that things are in the right place. In the case of VSMP, this is page level locality. And so the sort of support that is necessary is to help people understand that. This is another of one of 2 slides from Mike that he didn't use, and this is just emphasizing why we think it's worth putting flash memory into there. So if you go down the hierarchy and look at the programming paradigms and the relative speeds from registers right down to spinning disk, there's this latency gap sitting above spinning disk. And so, like with Gordon and I guess Comput to some extent, we've bridged that with flash drives. So when we went out to the Australian Research Council and asked for funding for a new machine, like Gordon, we put this up as a couple of major innovations. One of them is using these high throughput solid state disks. I'll give you some numbers on that in just a moment. We put very large amounts of main memory into this machine, more so per node than in Gordon, to try and get the balance between when you use VSMP for gluing the nodes together and when you don't. But then we put the software shared memory, the VSMP product in there as well. We had a number of chief investigators in the proposal and drew on a few different application themes. So they are directly manipulating large amounts of data. We have another driver which is integrating observational data into the computation. So as the computation proceeds, you can be streaming real-time data into that and nudging it. So if you know anything about climate models and weather models in particular, you know that they get nudged by real data from sensors. So that's the second driver. Problems that require very large memories to operate efficiently, and then as Mike has highlighted with the computational chemistry, there are problems that just do a lot of temporary storage and very small files. So that's unexpected for use for SDSC, but fortunately not for us. We now expect this in the load. So what is FlashLite? It's 70 compute nodes. There's about 1,600 cores of Haswell processors in there, so we're processor generation past the Sandy Bridge. We've chosen to put a very large amount of memory per node. So of those 70 compute nodes, there's 0.5 terabyte of DDR2 memory. Now some people look at us and say, wow, that's brave. We really want to cater for applications that may have a small number of threads that manipulate a large amount of data. And we know that in genomics, these tend to use multiple terabytes. So then in gluing these together with VSMP, we're keen to glue together as few as possible. So we know that we can move from 0.5 terabyte machines to 1, 2, and 4 terabyte machines up to aggregates of 4 terabytes, and then execute those de novo reconstruction jobs, and then tear them down again. One of the things we learned that when we were profiling for Gordon was, for FlashLite, was that users often say they want the memory, but don't necessarily use it. So we can reconstruct the machine dynamically around that. So that's one major shift, I suppose, away from Gordon, is to put a lot of memory per node. The other one is that we don't have I/O processors. Now you might say that's a bit strange because a number of the wins in Gordon were around having I/O processors, but almost every node in our machine can behave as an I/O processor. So we've got three 1.6 terabyte NVMe drives on each node. So that's nearly 5 terabytes of flash memory per node, all in InfiniBand connected with a parallel file system out there. And storage for us is a separate issue. It's handled by the RDSI and Nectar storage. So the trick will be how much of that can I pull into the flash drives and then operate on multiple times. So we've fiddled a few of the parameters there. It's an experiment as well. We'll see how well that goes. But that comes out of some of the discussions with San Diego about what might behave a little bit differently. We also have not run ScaleMP, VSMP across the whole machine. So I think one of the lessons that Mike highlighted there was that it's very unlikely you're going to take over the whole machine and run distributed shared memory across the whole machine. And so programs of that class tend to be distributed memory message passing type programs, and we can run those. So the ScaleMP to a large extent is giving us the RAM aggregation as much as the CPU aggregation. And so there's a slightly more schematic view of what it looks like. It's multiple racks. In fact, in the last slide, there's a picture of it down at the Polaris Data Center. This is hosted off campus. It's hosted next to the cloud. It shares the networking of the cloud, and it has direct access to the storage subsystems out there. So it's multiple racks. You can see there a couple of nodes on the right-hand side. There, as I said, there are 3 NVMe drives in each node, plus a SAS drive, and an InfiniBand connected dual rail InfiniBand network at the top there. So we've split the ScaleMP traffic and the message passing traffic in that machine. So I won't dwell on this. These are some slides from ScaleMP, but we can construct a machine that effectively you turn the processors off and access this very large memory. And we imagine that being used in some of the computational biology or bioinformatics codes. We can run shared memory. So each node is dual socket Haswell boards, so you can have up to 24 threads per node with half a terabyte each, and then aggregate those up, as I said, to the 4 terabyte level. And what the VSMP software does is allow us to have that appearance of a single system image. So it virtualizes the processes. The operating system thinks it's seeing all of the processes across the supernode. It's also seeing all of the memory across those. Question for the last slide there is, how do we want to think about this? And this is what I really would like to encourage people attending the workshop to be thinking about. I don't imagine you get your codes going this afternoon, but think about this machine differently and talk to us about how you can use it. So if the codes you're running are very large memory, think about having the whole structure in memory. If it's a graph, think about the whole graph being there. If it's a database, think about the whole database being in memory. This is a different way of thinking about problems in which traditionally we've tried to partition them and get them in and out of storage, of secondary storage. And as Mike's pointed out, we can mount RAM disks in memory. So even if the code has got traditional file I/O, we can build RAM disks in this memory. And remember, we've got quite a lot per node, and so database access could be extremely fast there. So that's the memory view of it. From an I/O perspective, again, RAM disks in memory. Well, that's just the I/O. We've got 5 terabytes of flash storage per node, and we haven't worked out how to configure that yet. So we've got 3 by 1.6 terabyte drives. We could present those as temp file systems. We could present them as rated up. I think we're presenting them as burner. I think we've got them as 4.8. Single file system, RAID 0. We can also, they're also visible within the supernode. So all of the drives of the boards in the supernode are visible as drives to this one operating system. So we've got a lot of options there. And you really shouldn't take it as assumed that we know what to do with those. So we want to hear from users about, well, if I could do this, if I could put the database on this drive and something else on another drive. We want to hear about that. So we've got a lot of options, but absolutely think about databases in SSD. As I said, every node in FlashLite can behave as an I/O processor. So if database access is the thing, then there's a lot of options there. And then finally, I think Mike pointed this out, it's still a fairly substantial compute cluster. So yes, we've put a lot of memory per node, but at the end of the day, there's still 1,600 Haswell cores, and that's a sizable compute resource when you add it to the already existing cloud infrastructure we've got at UQ for doing high throughput. So that's where I wanted to leave the discussion. I think, Mike, you've given us an excellent overview of thinking about different application threads and how they can map to it. FlashLite is a little different, apart from being a lot smaller. And the Research Computing Centre is very much there to help people use this machine.